dam break flow analysis, and let us see what is there. So this is the plan of my presentation. I will briefly introduce the topic, what is dam break flow, why after all the dam should break. As an engineer I should design it very strong so that the dam does not break. I will introduce you what is this topic, and then for today's presentation I have selected, there are several tools, individual tools, but I have selected GIS because GIS is freely available, it is a software freely available. So I have selected GIS for my this schematic diagram represents a reservoir, which is the blue shaded portion, a dam, and downstream is the river. Okay. And there may be several reasons why a dam will break. Maybe your enemy during wartime would like to bombard your dam. You see history during Second World War. It was a strategy by Hitler and his friends that don't harm your enemy, harm their dams. Okay? So the dam may break, but as an engineer, what is our point of view? The important thing for us is, if the dam breaks, remember the starting point is, if the dam breaks, then what? Then for us the important thing is to know what is the flow depth or the water level at a downstream location. Maybe my city is located 40 kilometers downstream of the dam. So in my city, what is the expected highest water level due to this accident? And the second most important thing is, what is the time of travel? Because if you see the disaster management programs, all flood related disaster management programs, they take into account the lead time. If you can predict that yes, now after 6 hours there is a problem which is coming to you, or after 3 days the problem is coming to you. Accordingly, we can select our disaster management plan. For example, evacuation of the place. Maybe we will bring all the people to a safe place. Okay? So this lead time, how much time it takes for the flood wave to propagate to the desired location is extremely important. Next. This is the difference between a normal flood, because due to heavy rainfall also there may be flood. So this is the difference between rainfall, the flood due to heavy rainfall, and dam break flood. You will see the red curve which is due to dam break flow. You can mark the peak discharge and the time to attain the peak. In case of normal flood, the time to attain the peak is higher. But in case of dam break flood, because all the reservoir water is rushing into the downstream channel and it is like a mega flood, so the peak of the hydrograph is very high, the time to reach the peak is very low. That means it is a relatively more serious problem. Right? There is also something called the levee bridge. Dam, as we know, is perpendicular to the flow, a structure perpendicular to the flow. The dam may break. Similarly, on the side, if a channel is flowing, on the side the dam may also break, which is levee bridge. If you remember 2008 Kosi flood, it was a levee bridge. The river is coming from Nepal and Kosi barrage is in Nepal, but Indian engineers are in charge of its maintenance. But unfortunately, on the side it broke. So it was a levee bridge. So in literature, usually we find dam break flow and levee bridge flow. We treat them equivalent. Okay, next. These are some instances. If you do it, you will find more and more instances. I would like to cite the second one, which is Pradhan dam break. Pradhan dam break failure was in US, and it is special because some measurements were taken. Remember, when the dam breaks, because of its ferocity, no engineer will be there to take measurements. But in Pradhan dam break failure, there was some measurement. But these days, you know, sensors are available. You can put your sensor, you will not be present there, and your sensor will take measurements. Those kind of things are. These days those things are available. And I would also like to mention something called the cascade failure. In a river you may have series of dams. Okay. One dam breaks, the flood wave goes and hits the second dam, it may break. So in Italy there was once 7 dams failed. Okay. This is called a cascade failure. Any dam break flow in India, if you see history, Pasupuleti in 1979 in Gujarat. The dam break flow. If you see also newspaper or Google 2023, there was an incident. There was a dam break. Let me also tell you, I have some slide to show, but let me tell you that in today's viewpoint, our government has topmost priority for dams. And they are spending quite a lot of money for dams. Let us go. Yes, some more pictures. This is from Libya. And pictures. We all know how the pictures is dam break. These are the causes, and I have not noted down here all the causes. There may be several other causes of dam break, but some of the more familiar causes are overcoming. When we design, no dam is designed for overcome. We design in such a way. If you are from civil engineering background, I am sure you must have calculated something for in your project, in your details. We calculate different forces acting on the dam body, and then depending on whether it is an earthen dam or whether it is a concrete gravity dam, depending on that, we design it so that it can withstand different forces. However, no dam is designed for overcoming. We always assume that the stored water level is way below the top of the dam. We keep something called the freeboard, something like 1 meter free space we keep in the reservoir. There may be piping failure. I have some picture I will show you. So what happens is, if it overcomes, if the flow from the reservoir goes on top of the dam, the stress at the downstream corner will be very high and the dam may rupture. Piping failure is, if especially in case of earthen dam, there may be some weak zones. Okay? So because of seepage, some water may find its path to the downstream side. Initially it may be, the size of the pipe may be of nanometer size. But as time progresses, and from outside we cannot know anything. As time progresses, this pipe size increases and eventually it grows and eventually the dam breaks. Okay. And there may be several other causes like design defects. To err is human. So as human beings, even if you do your design using computers, whenever we use computers, usually we think that it is foolproof. No. Man is the boss, not the computer. So being a man, we may commit some error in our design process. Poor workmanship, earthquake, and remember the first point I mentioned, bombardment. Okay. There may be several other reasons for dam break. What I mean to say here is that, for example, I may take the consultation of the wisest doctor in the world, but one day I have to dam being a structure, I may design it very strong, but being a structure, eventually it has some life, some finite life, and it may. These are some of the applications. Primarily, if we see these days, we all go for multi-purpose dams. Whether it is power generation or whether it is irrigation or flood control. So many kinds of multi-purpose dams. But because of the dam, there is a factor of safety. People come closer to the dam. And now, if the dam breaks, there is a. Okay. So it is a disaster, and these kind of studies can be applied for design of spillway, for flood disaster management program, like the risk or the hazard mapping of the locality can be done using this kind of exercises. The reservoir operation policy can be obtained. Design of structures in the vicinity. Suppose there is a building close to the river, so the building should be designed based on the fact that if there is a dam break, if the flood water hits it, then what will happen? Currently, in fact, this work is in progress. Currently, I am dealing with a nuclear power plant. Due to confidentiality rule, I cannot disclose the name of the plant, but I am doing a dam break analysis for that. Why? Because it is located near a dam. If the dam breaks, and they are now going to set up a new unit for that. So if the dam breaks, is there any danger? Is there any chance that the flood water will hit or not? That kind of a situation. If there is a school, there are buildings, we must design those things considering the dam break. Please let me tell you here that when it comes to disaster, usually we consider earthquake as the disaster. Usually we consider fire as the disaster. Flood, yes, we also consider as a disaster. But if you see the frequency, earthquake happens, I am not saying which is good, which is bad, or disasters are bad. So, earthquake if you see, then it happens only at selected places, not every place. If your zone is under active earthquake zone, your place is under that, then only it may experience earthquake. So, the buildings should be designed against earthquake. Similarly, for fire, you will find a very well-defined code. Our IS, Bureau of Indian Standards, they have published building design codes. Codes for fire safety, codes for design of a building against fire, design of building against earthquake, you will find. For flood, you search and then let me know. For your kind information, there are no standards for design of buildings against flood. Whereas flood happens almost in all the states, every year. Okay? So flood is a very, very important topic. So these are okay. So I would like to mention this war strategy. During Kargil war, I did something, of course not on my own, on the request of Indian Army. I did something Indian analysis. You know, everything is fair in love and war. We have international rivers, and those rivers are boundaries. During war time, our neighbor would try to come crossing the river. The gangs will come to the other side, to our side. So if we can operate our dam gates such that the river will act like a barrier, natural barrier, it will have sufficient current, velocity, then the gangs cannot come to this side. So that kind of analysis I did. So it is a very well-known work strategy, dam gate analysis. Okay. Here the dam is not broken. If the dam is broken, then all the water will cross. Okay. You have the gates, you operate the gates. So using your tools, you can also simulate these kind of flows. That if the gates are operated in such and such way, till what day I can sustain this kind of condition. Next. So this is International Committee on Large Dams, an international body. They make it mandatory that one must perform the dam breakthrough analysis for all. I have mentioned here large dams. The number is, if your dam is higher than 50 meters, you have to conduct the dam breakthrough analysis. Whether it is an old dam or existing dam or a new dam or a dam which is coming in future, you must do it. This is the law. Let us go next. So on behalf of that, we we have this Dam Safety Act 2021. Please go next. It says, I have just taken here some selected portion. It is a very long paper. So legally we are bound, the dam authority is bound to conduct the dam rate flow analysis. What all I am trying to say here is, this dam rate flow analysis is very important. It says every owner of a specified dam for each of its dam shall carry out risk assessment studies at such interval as may be specified by the regulations, and as such studies shall be made within 5 years of the date of commencement of this act. And started in 2021. Many of the dams, they have not yet done it, and works are coming. Usually in our scripture they say that if you self-praise, it is like a crime equivalent to suicide. If I praise myself, it is like I am committing suicide. But still, I am supposed to be the best person in dam rate flow in our country, and many works are coming to me because it is mandatory that a dam authority has to conduct a dam rate flow analysis. Let me also tell you here that when I joined NIH Roorkee as a scientist, my first assignment was to do the dam rate flow analysis for Manchi Dam, which actually happened. In dam rate flow analysis, the third part is you do not know how the dam will break. So then how to do the dam rate flow analysis? As I said in the beginning, the starting point is if the dam breaks, but I do not know how the dam breaks. For example, if the dam breaks, whether it takes 2 hours or 2 days, I do not know. What kind of analysis? So usually we do a hypothetical dam break. That means the user, based on his wisdom, decides what are the different factors and accordingly does the dam break flow analysis. Meaning he or she creates different scenarios so that we can find out the inundation area. That means which area is under threat or under risk. Let us go to the next thing. So these are the risk factors, therefore we must do the dam rate flow analysis. So these are some of the classifications. Go to the next. Yes. So small dam, intermediate dam, large dam, as I said, I code suggests that I code is for large dams, but it suggests this dam rate flow analysis should be done for all dams higher than 15 meter. If dam rate flow analysis is such an important topic, then how it is done? It is not that we are doing it for the first time. Okay. So it is done by analytical methods. There are analytical methods. If you see literature, the first dam rate flow analysis was done by something called Ritter, and it was in 1857. What was that? He assumed just a flat plate, another vertical plate. On one side there is water, the other side no water, and this plate was suddenly removed. Now this water cannot stand, it will move, and he called it dam rate. Of course, our real life dam rate flow is much different, because no dam is one dimensional like a thin plate. It is a solid 3D object, and no dam is completely broken. When it breaks partially. Some part of the dam will break, not the entire dam. Okay, so there are, when we compare with real life dam rate flow analysis, there are differences. But what I am trying to say here is that dam rate flow has been studied even 1857. Okay? So analytical methods are there, experimental methods are there. If you have a lab, very good hydraulics lab, you can prepare a channel, you can build a dam, and purposefully you can break it and see how the flood wave provides transfer. Okay? And of course you must have your measurement devices, sensors and other things. But numerical models are very important. Why? Because it is user friendly, because it is less time consuming, and also it is kind of cheap. If you are to conduct a very good experiment I can imagine your expenditure will be of the order of 1 crore rupees, not less than. But if you are conducting through a computer model, what you all need is a very good computer, maybe a workstation. And as I said, GIS is free of cost. You download it and you have to learn something in YouTube, many tutorials are there, you just learn it and then run your model. So maybe if you have a friend who knows it, from him or her you can learn it in 1 hour, 2 hours, or maybe you can give me a top of the value. I can teach in 1 hour. Why not? So it is cheap, okay, and very convenient. Of course, I belong to the old school of thoughts. I always think that experiments are better, which may or may not be correct. But when you conduct experiments, you know the physics. But in these kind of things, you have to see numbers, and from the numbers, you should try to visualize the things. Yes, the third wave propagates and things like that. Anyway, so my topic, as I said, this is in order of complexity. Same-Hannan equation is supposed to be very simple. Gaussian's equation is more complex. Navier-Stokes equation is even more complex. So in today's topic, when I talk about GIS, it is the Same-Hannan equation. So today's topic is concentrated on Same-Hannan equation. These are some of the challenges. Because anybody can write a computer program, but it is not so easy for dam break flow, because in case of dam break flow, the flow is highly turbulent. Turbulent, you know, like a cigarette smoke. Where it is going, you do not know, Brownian motion. So the water propagates with turbulence. Very difficult to predict. And not only that, presence of a soft wave. Okay, soft wave means if you see the water surface profile, there is a discontinuity in the water surface profile, like hydraulic jump, moving hydraulic jump kind of thing. So not all the computer programs can capture those kind of shocks. Okay? So therefore these are some challenges. Other challenges are river bed erosion, because with such a high kind of flow, the river bed will also erode. And the dam breach process, which is a completely geotechnical engineering thing, we do not know much of that. As I said in the beginning, the user will assume that okay, it will take 2 hours for the dam to break. Why 2 hours? Okay. So the understanding in dam breach process itself is a difficult. Therefore, these are some of the challenges. So next, these are some popular softwares, DAM, V.G.K, very popular software, free again. Okay. This GIS is free. I11, I21 is commercial software. I series IC. Now it is available in IC. Flow2D is again free software, very popular in US. Fluent and Flow3D both are commercial softwares, but the specialty of the bottom two are that they are CFD softwares. Meaning all the other ones they use Same-Hannan equation, whereas the bottom two they use 3-dimensional Reynolds average Navier-Stokes. So that is the difference. Which is better? Usually we think the bottom two are better because 3-dimensional flow, but actually the thing is not like that. So when you use CFD, you can use a domain like 1 meter, 2 meter, or maybe 10 meter. But you think of the real life situation. When a dam breaks, the propagation is not limited to 1 meter, 10 meter. It is up to kilometers. So when you consider kilometers, these two things are not so efficient. Maybe GIS is very good. Let us go ahead. So as I said in the beginning, I am going to use in my talk GIS and dam break flow analysis by GIS. Anything you want to ask now at this pause. I know anytime after launch is very difficult to concentrate, but in case there is any question, any comments, till now whatever we have discussed, feel free to ask. Alright, let us go next. Why GIS? Because as I said, it is a free software available in the public domain. You can just copy this address and download in your laptop. This was developed by US Army Corps of Engineers, and it can do, in fact, all kinds of hydraulic analysis. This RAS, name RAS, stands for River Analysis System. So any kind of river flow problems you can handle in ACAS. You can prepare the inundation map. You can also study not only the dam break flow case, but any kind of flood propagation, any flood routing, steady flow, unsteady flow, sediment transport, many rivers combining, so confluence, those kind of things also can be studied next. These are some other tasks performed in ACAS when we conduct the dam break flow analysis. These are the byproducts. The flood wave propagation and arrival time we can find out. Integration with GIS for better visualization. When I was taking my first class in taking means I was studying, somebody was teaching me. The first class in computer programming. In computer programming, we must remember three things are important. One is the pre-processing. It is like preparing your sabji. You need to cut vegetables and other things. Prepare. Okay. Before you actually prepare the sabji, you need to do some pre-processing. Then the actual process, that cooking process. Then the post-processing. So if the sabji is ready, that is not enough. You may like to add some maybe coriander leaves or make it beautiful before you serve. And when somebody eats it, that is the complete process. Similarly here, the pre-processing is required. The actual running or execution of the programming is required, and after it runs to analyze the results, which I call as post-processing, that is also essential. So these are different things which we can do in ACAS. Calibration and validation with historical data, scenario analysis for emergency action plans. Remember in dam break flow analysis, if I do the dam break flow analysis, then what? Then it can be used, the results can be used for emergency action plan. Okay? Risk assessment and impact analysis, those kind of things you can do using this, because now GIS is associated with ACAS. So using those tools you can prepare different maps and then use those maps for your emergency action. Next. So this is the sequence in ACAS. Okay? If you see the manual, everything is there. If you see the tutorials in YouTube, you can know. And I also mentioned or suggested you can also ask your friend who knows ACAS. But primarily, the main things are these four. Okay, number one, if now imagine there is a dam, a reservoir on its upstream side, and downstream side there is a channel. So the first thing is, if due to rainfall, some flow is entering into the reservoir, how that flow will reach to the dam, or how that flow will reach the reservoir. I call it reservoir dam. Okay. Then number two is the dam break process itself, meaning what will be the bridge size the user has to give. Okay. How much time it will take, how much depth it will come when it breaks. I have some figures I will show afterwards. How much level it will avail, it will reach what level. Okay, those kind of dam break simulation is done by the program, of course based on the data provided by the user. Number three is release from the reservoir, meaning now if there is a breach, now reservoir water is at some level, how this reservoir water level will be released to the other side. Okay, and the fourth and the most important one is the flood routing in the downstream channel. So these four sequential steps constitute the dam break flow analysis. Next. So for reservoir routing, if you have studied in your hydrology, basic hydrology book, there are several methods. there is something called the Paul's method or the modified Paul's method. Both methods you can use. ACRAS uses, this is modified Paul's method, the first one. This is a hydrologic flood routing. Okay. You can remember this way. Suppose some water is moving on ground, on the table, let's say. If that is the thing, then it will offer some resistance. The bed will offer some resistance. But reservoir being a water body, okay, if the flood wave propagates on that, what will be the resistance? Resistance is very negligible. And the flood wave will propagate very fast. Using those principles, we don't go into details of hydrodynamics and we do a flood routing kind of a thing, called as the hydrologic way of doing the flood routing for reservoirs. Also another option where you can use this independent equation, I have written here as full dynamic routing method. Okay. Next, and as I said, the dam break simulation. The dam break simulation. Next. So I have given here two different kinds of failure. Okay, it can also be through other means. For example, in the overtopping failure, you mark the left side figure. It starts, although I have the first thing was shown as a trapezium, but it starts as a point. At t is equal to 0, if I say to the program that now the dam break will happen. Also note that the user is to provide some criteria of dam break. For example, when the reservoir water is same as the dam stock level, dam break will initiate. That kind of a thing is to be provided. Okay? And the dam break will start as a point. That point will eventually grow as a trapezium. And that trapezium will further grow. And whatever time, let's say I give 2 hours. Okay? Usually it depends on the material. If it is a earthen dam, it takes something like 2 hours, maybe 3 hours, 10 hours, depending on the characteristics of the earthen material. But if it is a concrete dam, usually when they construct the dam, it is based on some slabs. So one slab will be removed. So it is very fast. Something like 5 minutes, 6 minutes, that kind of a thing we give. Okay? So these are different failure procedures, and this information is to be provided to the software. Accordingly, the software will simulate the dam break process. Next is, you can see here, mark on the right hand side, the initiation is something through a pipe inside the dam wall. Okay? And through that, the reservoir water is going to the downstream side. So this is again to explain you with time how it propagates. It starts as a hole, but eventually it increases. Go to the next. So these are the 3 most important bridge parameters that we must provide as user to ACRAS. One is the average bridge width. So if it is a trapezoidal section, suppose after the dam break process is completed, this is the final say. Then this width plus this width divided by 2 is the average width. When it asks for average width, we have to provide that width. Okay? The bridge elevation. Similarly, top of the dam we know, but whether it reaches the bed or somewhere it stops. Why? Because as the bridge section develops, the reservoir water is getting released. Okay? That means after some time there is not much load on this bridge because most of the water has already been released. Therefore, it will attain something called the equilibrium or the final bridge level. The third and also most important thing is the bridge time, how much time it takes. As I said earlier, depending on the dam material, whether it is concrete, usually for concrete we give 10 minutes, 6 minutes, 5 minutes, something like that. Okay. Please note that it was developed by US. So by default, the units are slightly different, like miles, not kilometers. For this, it is hour. So if you are saying 6 minutes, then you have to give 0.1. So bridge time, all these three parameters are to be given next. So as I said, in the sequential steps, the third step is the reservoir readings. Now, knowing the reservoir water level and the bridge section at a given point in time, the program uses a broad crested weir formula to calculate the discharge from the reservoir to the downstream side. Okay. Not only the bridge section, also if this is your dam top, throughout the dam also there may be some spilling. Okay. So that is also used to calculate what is the discharge. These are the things for which the discharge is calculated. Spillway. Spillway is inbuilt in the dam. So what is the discharge? Because during this it is expected that all the gates will be fully opened. So through those gate openings, what is the water going to the other side? Then through the bridge section, through the dam top, and other, there may be, you may have a different passage. For example, let's say for power generation, you may have a tunnel which is used for power generation. So that discharge is to be also calculated. So you take into account all the discharges and then find out what is the discharge as a function of time just at the first section below the dam. So it comes to the fourth sequential step, which is controlling downstream channel. So like any other mathematical models, what we do is a physical process is explained through some governing equations. In my initial slides, I showed that governing equations could be anything. If you see literature, there you will find hundreds of governing equations. Okay. So here in Negras, this talk is primarily about 1D modeling, also 2D model. That address I showed you, Negras version 6, that has also 2D models. Okay. So in 1D model or 2D model, it is the same kind of equation which is used in this case, Negras. So governing equations, then it uses an implicit finite difference scheme. I am not going into the details of mathematics of these things. Okay. But there is something called implicit scheme. Implicit scheme is used to solve these partial differential equations. Note that these partial differential equations are hyperbolic equations by nature. Therefore, appropriate numerical method is to be used. Initial condition is extremely important. Boundary condition is important. If someone of you have already done Negras, usually we have a tendency to use normal flow depth at the downstream end, which is not correct. At least not correct for dam. One should use a different kind of boundary condition. Most appropriately, if there is a measurement station, gauging station, then use the measurements from that side. Or if there is a locality where you have the rating curve, for different locations we develop rating curve, which is Q discharge versus H versus Q. If you know that, there are several options in the menu in the graph. Normal depth is a very simple option and that should not be used for dam depth analysis. So boundary conditions, then other channels, if other channels are joining, that should be taken into account. Then other structures, like there may be a bridge, there may be a barrage, okay, downstream, or there may be maybe a canal which is extracting water. So all those things can be included in the analysis. Next. So these are the governing equations. As I said, I am not going into details of these equations. If you want to know more, you have to see literature on this. But let me tell you just one thing. This A and A0 means it is like your car lens. Okay. The reverse section is like this. Here it is like this, and as I go up, it will spread like this. We call it a compound section. So when the flow takes place, in the middle, it will be high speed car. But here it is moving, but relatively less speed. So A0 is inactive area. So everything is area. A is active area, A0 is inactive area. Next. So these kind of practice we use. For example, we take these green dashed lines. They represent different cross sections, and using these cross sections, we try to apply for these cross sections the governing equations. We solve the governing equations for these cross sections. That way, we do the flood. The first part is the reservoir, then the dam, and then the river. Next. These are the inputs we need to conduct a dam breakthrough analysis. The topography, meaning not only the river cross section, we also want what is there, because when the flood wave propagates, it will also go to the sites. So whether it is grass or building or vegetation, we must provide those information. How? Through Manning's roughness coefficient. These days you don't have to worry much. Some database are available. You use GIS, you prepare the map of the locality, and for each block you divide your study area into different blocks, and for each block you can assign a number of Manning's roughness coefficient. Grid size you have to give, time scale size you have to give, dam details you have to give, what is the top of the dam, what is the spillway, how many gates are there, all those information is to be given. And most importantly, as I said, broad-crested where formula is to be used, you must give the coefficient of discharge for the broad-crested where, and that is not a unique value. It is not that it is available and it is applicable to all kinds of shapes. Breach parameters, as I already said, those three parameters, and there may be other requirements. It is very difficult to remember for anyone what will be the inputs. You just punch the keys, see on your terminal what is required, and as it asks, as Hecras asks you that you provide me this information, you provide those information. These are some broad ideas about the input parameters. Next. So these are some of the outputs. Well, there is no need to read this, or maybe I can read this. The arrival time of the flood can be obtained, maximum water level can be obtained, time of peak water level, maximum inundation area, flood depth, flood velocity, flood duration. The most important idea is, if you look at the governing equations, your dependent variables are two. One is discharge or flow depth, you can also say. The second one is the discharge, the velocity. Okay. So let me repeat: flow depth, okay, and velocity or discharge. So you can obtain these two parameters. All these are, it is like you eat rice and also you have some side dishes. It is like this. Again, an important thing is that it can give you the flow depth and the velocity. From those two things, you can always find out all these assessments. Whatever is required for you, you can find out. For example, suppose I want to prepare the flood inundation map. What should I do? I should find out what is the water depth. From that, I can find out what is the water level, and use that water level and see in the contour map in which place it is propagating, and that is your inundation area. Next. These are some of the concluding remarks. Dam breakthrough analysis is an important hydraulic exercise. It can be performed efficiently by Hecras. There are several numerical tools, but Hecras is very popular. You can use the quick confidence. Hecras is freely available and is user friendly. Why it is so popular? Because of its associated graphics. You can see your results in different varieties of ways. Results from Hecras can be used in disaster mitigation plan to do dam breakthrough. Next. So these are some of the references. Yes. So currently I am leading the Narmada River Basin Management Plan. This is a Government of India Ministry of Geospatial project, which will be for at least 10 years. And you know about Narmada River. Narmada River has many dams. God forbid, let us pray that there is no dam break in the river basin. But these are some hypothetical studies. Meaning, if the dam breaks, what will happen? Some This is another beautiful side of a class. You can prepare movies and you can see your results from this. So this is for Barbi Dam, this is for Tawa Dam, I have two other dams. Like this would be next. This is Indira Sagar Dam, this is Sardar Sarovar Dam. You must be knowing Sardar Sarovar is the Narmada Canal and the Narmada River in Gujarat is called the lifeline of Gujarat. Gujarat is historically, traditionally it receives very scanty rainfall, very less rainfall. But due to this Narmada River and Narmada Canal, we get drinking water and whatnot. So, this is some of the studies. With this, I will conclude. I will stop here. If there are some questions, feel free to ask me. I will try my best to explain it in a very simple way. If you have no questions.